Okay, salam, hello everyone. So let's proceed with the lecture here on the MOSFET AC analysis. So we have done DC analysis in our previous lectures. So we are going to build from the DC analysis to extend to AC analysis. Okay, so first of all, you need to understand the E-MOSFET AC equivalent circuit. So we have the symbols for the PMOS and the NMOS, okay, the P channel, N channel, E-MOSFET, and the device itself can be represented when we do AC analysis, can be represented as a small signal AC equivalent circuit, or sometimes called the mid-frequency AC equivalent circuit. Okay, so this is called the mid-frequency, okay, mid-frequency AC equivalent circuit, or sometimes called a small signal AC equivalent circuit. Both are the same meaning. So here basically we have the gate terminal here, we have the source terminal, and we also have the drain terminal up here. Okay, so this particular model we can represent using a new model for AC analysis, and this is called the hybrid pi model. We also have a different kind of model, but for our class we are going to be looking only at the hybrid pi model for the AC equivalent circuit. Okay, so what are the components in the small signal mid-frequency circuit is we have three components here. We have VGS, we have GM, and we have the RDS, and we have a voltage control current source, GM VGS, going down. So in order to know the value of the current, we need to find the values for GM and VGS. So VGS is basically calculated in our DC analysis, which is the VGSQ. So here we can say it's a VGSQ. GM and RDS, these are new variables that we have not looked at in our DC. So we're going to look into more details. What is actually GM and RDS, and how we can calculate them. So GM is known as the transconductance, okay, the transconductance of the MOSFET, and GM can be determined from the graph, but the equation is simply that GM is the rate of change of the drain current ID over the rate of change of the VGS. Okay, so GM is the rate of change of ID VGS. So if you can see in this figure, this figure is actually for JFET, but it's quite similar for our E-MOSFET. So in JFET you have VGS off, you have IDSS, and you have the curve here. So this curve here is similar to our E-MOSFET. So for example, in our E-MOSFET we might have a load line. Okay, we might have a load line, we've seen already from the DC analysis, and we have the Q point right here. And if we take the rate of change of ID over the rate of change of VGS at the Q point, we can find, or we can calculate the value of the transconductance GM. And we know the equation for ID for our E-MOSFET. We know that the ID is actually equals to K VGS minus VGSTH squared. So then we can take the derivative of DID over dVGS is actually equals to GM. Okay, at VDSQ. Okay, so if you have the ID equation, you can simply take the derivative ID and VGS, and from there we can get our GM. Okay, we will see more analysis of that later on. And then the RDS. So what is RDS? So RDS is in fact the MOSFET output resistance. Okay, internally to the MOSFET, which is located between the source and the drain terminal of the MOSFET. Okay, so if you think where is the drain and the source, so we have a resistance between the drain and the source, which is called the RDS, and normally it has a high value. Okay, we can approximate it. Okay, which we typically do is we can approximate it to be equals to infinity, a very large value. So because of RDS is large value, we can normally neglect it. Okay, in our small signal analysis, in our circuit analysis here, we can neglect the RDS, but in fact it can be calculated from the drain source characteristics. Okay, so what is a drain source characteristic graph? So drain source is the ID VDS graph. Okay, we've seen this in the previous videos. So if you have the ID VDS graph, the RDS is simply ID, okay, delta ID, the change of ID versus over the change of VDS. Okay, and if we for example, if we have a straight line, okay, approximately straight line like this, then we can say that our delta VDS in this case is probably close to infinity. Okay, so what happens if our delta VDS is close to infinity, then our RDS will be also infinity. Okay, regardless of the value of ID, and ID is typically very small. The ID is typically very small, but in the end we can actually approximate RDS to infinity. So therefore the resistor can be neglected. Okay, let's go back to our GM calculation here. So we know this equation already from our previous lectures. ID equals to K VGS minus VGSTH squared, and GM is simply the derivative, okay, the derivative of ID against the VGS, the ID over dVGS. And if you take the derivative, we're going to get GM is 2K VGS minus VGSTH. Okay, and we also know that VGS minus VGSTH is actually square root of ID over K, and this one is actually coming from here. Okay, if we take out our VGS minus VGSTH, we're going to get square root of ID over K. Okay, and from there we can substitute this inside here. Okay, substitute the square root ID over K inside the GM equation above. Okay, and finally we can prove that actually our GM is equals to 2 times the square root of K ID, and ID here is you can use the IDQ, okay, the IDQ that we calculated in our DC analysis. Okay, and K can be calculated using our K equation that we have seen in the previous lecture. So using the K and the IDQ values, we can calculate our GM. Okay, so MOSFET configuration, there are several MOSFET configurations, but for this class, we are just going to cover the common source MOSFET configuration. So what it means by common is that it's grounded. Okay, so common means grounded. So if the grounded source or the common source that we're going to cover, so this one is not covered here. Okay, so not covered in our lecture, will not be in your test and exam. We are just going to look at a simple, the most common one, okay, the most common for MOSFET, which is the common source configuration. Okay, so let's look at the common source. So remember that the common source here, common source amplifier, it means that we are grounding the source, but we can have a source resistance or without a source resistance. That's an option that we can have. And another characteristics of the common source amplifier is that the input is given on the gate terminal of the MOSFET. Okay, so input is here. So you can see that the input is actually provided on the gate, and we have a grounded source terminal that may or may not have the source resistance. And then here this circuit, also another characteristic of this circuit is it has a bypass capacitor. Okay, so where is our bypass capacitor? So this one here is our bypass capacitor, and we see later on what the purpose of the bypass capacitor there. So we can have, or some circuits we can have a bypass, and some circuits we can actually remove and not have the bypass. Okay, so in this case we have a common source amplifier with a bypass capacitor without RDS. So RDS is normally here. Okay, it's between the drain and the source. So RDS, which is close to infinity. Okay, between the drain and the source. So without RDS, we are going to remove this. Okay, we say that it's infinite. We replace with the open circuit OC. Okay, so this configuration here, and from there we want to derive the mid frequency or the small signal. Okay, mid frequency, or sometimes called the small signal AC equivalent circuit. So what is the step to obtain the small signal AC equivalent circuit? The first step is to replace source with ground. This is the first step. Okay, replace source with ground. So for example, here we have our VDD. You're going to replace with the ground. Okay. Okay, go back here. So replace source with ground. Replace source with ground. So here we only have one source. Okay, our source and the gate terminal here is already connected to ground, so no issue. So replace with the ground, and then number 2 is to short all capacitor. Okay, so that's step number 2. Short capacitor meaning that now we have a line here, we have a line here, and we have a line here. Okay, meaning that now the current can go through. Okay, the current can go through. So you can see that what is the effect on the bypass capacitor is that our current ID, okay, is now going to go through the bypass capacitor, and here will be gone. Okay, so the source resistance will appear to be disappeared or removed from the circuit analysis, but physically it's there. Okay, so once we have done this, and number 3, draw the AC circuit, AC equivalent circuit. Okay. Okay, so how do we draw? So basically here we can see that the RD here is connected to ground, and RL is connected to ground. RD, RL is also connected to the drain terminal. Here is your gate, here is your source. So we can see here that our RD is actually connected to ground. Okay, so ground. We have the drain, RD, RL. We have the small signal MOSFET model, JMVGS. We have the input now. Okay, and here if you see the source here, there's no RS. Okay, so no RS because we have the bypass capacitor taking out the RS. So we can also have the RDS here. Okay, so the RDS should be there, but in this case we're not having the RDS. We assume the RDS infinity. And we see here the gate here, the RG is connected between the gate and the ground. So we can see the RG here is between the gate and the ground. And then we also have this Rin. Okay, so it's called this Rin, or Rin is connecting between the gate and VS and connected to ground. So we can see the Rin is connected, or RS, okay, Rin or RS, gate, RS, voltage source, and to the ground. Okay, so basically we're just going to replace this middle part here. Okay, the transistor model, replace that and put all our resistance. Okay, so next we can calculate our input impedance ZI, output impedance ZO, and also the voltage gain AV. So where is our ZI, ZO, and AV? So ZI is here and ZO is there. So ZI is the resistance seen at the input. Okay, so the resistance seen at the input is simply RG. Okay, the resistance seen here, RG, and the resistance seen at Z out, okay, without RL. So without RL, without RS, the resistance seen at Z out is simply equals to RD. Okay, so Z in is RG, Z out is RD, and what is our AV? So AV is given by negative V out over V in, negative V out over V in, which is the voltage gain. Okay, how much V out are we gaining from a given input voltage? And VI, if you can see here, VI is in fact equals to VGS. Okay, so VI is equals to VGS. So we know that VI is equals to VGS, and V out, okay, is going to be the voltage across RDRL in parallel. Okay, so basically we have here is negative GM VGS, which is our current, RD parallel with RL. Okay, so we have a parallel RDRL, okay, on the V out times the current GM VGS, and here we can cancel this out, so then our AV is minus GM RD parallel with RL. Okay, so this is the voltage gain, and should be derived here, GM minus GM RD. So here we assume no load. Okay, no load. Okay, so if with load, then our AV is equals to minus GM RD RL. Okay, as we have seen here. Okay, as we have seen here, minus GM RDRL. Okay, with load. Okay, and here is without load. Okay, so I think that's all for this part of the video. In the next part of the video, we'll discuss some examples on more examples to understand the AC analysis for the E-MOSFET.